Hi, my name is Sayed from EDD Academy, and today I'm going to be covering Unit 7 on differential equations. First, what is a differential equation? A differential equation is an equation that relates a derivative of a function to other variables. Okay, so some examples of differential equations you may have seen are f is equal to mass times the time derivative of velocity, also known as f is equal to ma. dy dt plus f of t times y is equal to 0, very common differential equation. And this final one is from physics, bonus points if you know where it's from. Now, where are differential equations used? You want to know where the applications are. Now, differential equations are used to model almost any phenomena that involves change. Now, phenomena that involves change is very broad. It's in many different subjects. Examples are the sciences such as physics, chemistry, astronomy, biology, or in finance, right? So, like I said, these examples are physics, chemistry, finance, astronomy, etc. There are many more fields. Change is everywhere. Now, how do we model situations with differential equations? Now, in order to model a situation with a differential equation, there are two key things to identify first. Now, first is the derivative, pretty obvious, and the function. Now, this is stated in word problems or problems in general by saying the rate of blank increases or decreases by. Now, blank is usually the function, right? So an example is the rate that the population of rabbits increases by is, and now the population of the rabbits is the function that we're looking at and we're trying to solve for potentially. And the rate of implies a derivative. In this case, it's time derivative. However, look for what the derivative is taken with respect to, but most likely it's probably going to be time. Now, the proportionality relationship between the variables is also very important. Now, obviously, if it says equals to, that's pretty self-explanatory. You'll already have like a basis to set up your equation. But there are phrases such as, let's say, dy dt is proportional to y, okay? Now, that would mean that dy dt is equal to some constant, let's call it c, times y, okay? And if it says it's equal to some constant times y, well, I mean, even easier. Now, more broadly, there may be some phrases that hint at the connection between the function, the derivative, and any other variables or constants, but proportionality or an equivalence are the most important ones. Now, here's an example. The rate that a population of rabbits grows is equal to some constant c multiplied by the population of the rabbits at that time. Model the scenario with a differential equation. Because here's some key words. The rate equal to the constant c, the population of the rabbits, and multiplied. Here it is in math language. Population, the time derivative, and c times p. Let's put it all together. We got, finally, the time derivative of the population is equal to c times p of t. Now, as you can see, the rate that the population of rabbits grows, dp dt, is equal to the constant c times the population of the rabbits. This equation encompasses all of that. Another example. The rate that the volume of a cone changes with respect to time is proportional to the height multiplied by the radius times the rate of change of the radius. Now, in this situation, there are two derivatives here, each on a different function, namely the volume of the cone and the radius. If this was on a test, they would specify which is the main function you're probably solving for and which is a quote-unquote constant. What I mean by constant is that they would give you what r of t is equal to explicitly, or they would tell you what the derivative is, etc., etc. Now here's the answer. The volume of the cone we're going to represent with v of t. The rate of change of the volume we're going to represent with dv dt. The radius of the cone, similarly, is going to be r of t. The rate of change of the radius is going to be dr dt. Now, dv dt is proportional to h, the height, times dr dt times r of t. Normally, we'd write this as dv dt is proportional to each of these things individually, and then put it all together in this form. However, the problem explicitly tells us that it's equal to the product of these three things, so we don't need to go from that basic step to the step we're at right now. Now, since it's proportional to, there is some constant c that we have to multiply by the left-hand side to make it equivalent to. And voila, we got our constant. Here's the equation. We're done. All right, let's get another example here for some extra practice. Okay, so the rate that an amount of a radioactive substance decays is proportional to the amount. Write a differential equation that represents this situation. Okay, so let's get some notation out of the way. The amount of the substance will be denoted by A of t, and the rate of decay will be dA dt, right? Because this rate is going to be over time, and that makes a lot of sense, right? It's going to get less over time due to the half-life. All right, so it's proportional to the amount, right? So dA dt is proportional to A. And since it's proportional, there is some constant K that is the constant of proportionality, and multiplying that by A will give us the exact equation, dA dt is equal to K times A. This is an interesting situation because it represents an application of differential equations in chemistry, right? It's a pretty simple application, but still, the solution to this equation, as you'll see, is exponential, which makes sense, right? Radioactive substance decay is a exponential phenomenon. All right, next, we're gonna have a physics application. A ball thrown in the air is experiencing two forces, gravity and air resistance. Write a differential equation representing the total force on the ball in terms of the position, and specifically the position function. So for reference, air resistance is 1 half capital A times C sub D times rho times velocity squared. All that 1 half times A times C sub D times rho, that's all just there for like the actual physics, but for our purposes, we could have just condensed that into a giant capital constant C and just said that force is equal to big C times velocity squared. The velocity is what we really care about, but for the sake of accuracy, we'll just keep that in. The gravity on Earth is mass times g, the gravitational constant, and Newton's second law is force is equal to mass times acceleration. There's a bit more to this law which we'll actually use in the problem. Okay, now what's the answer? So first, we need to know that what velocity and acceleration are in terms of position. The velocity of a particle is the first derivative of its position function, and the acceleration is the second derivative of its position function. Okay, this will be very useful later on. So Newton's second law is specifically that the sum of all forces on an object, on a particle P, for example, is equal to the mass of the particle times its acceleration. All right, and we'll use this to set up our equation. So the force from air resistance and the force from the gravity is equal to the total force, right? According to Newton's second law. All right, we can just plug in our equations that we had from before. Okay, so 1 half A times C sub D times rho times velocity squared plus m times g is equal to mass times acceleration, since the total force by Newton's second law is mass times acceleration. And now, since we have our definitions from above, velocity is equal to the first derivative of time, the first derivative of velocity with respect to time, and acceleration is the second derivative of position with respect to time, we can just plug that in, and bam, there we go. We have our differential equation in terms of position. So this is actually a second order differential equation because the highest order derivative there is actually a second derivative. You won't be seeing a lot of these in calculus AB, but still, it's nice to have some experience in them. This is a good example of an application in physics, and as you've seen with these previous examples, differential equations are everywhere. Biology, chemistry, physics, changes everywhere. Alright, thanks for watching this video from EDD Academy. Be on the lookout for our future videos. Smash that subscribe button, smash that like button, and I'll see you guys later.